All right, the carry lookahead adder. One, I'm not going to make you learn this. Two, what's the point of this? Is to show you what goes into actually designing faster and faster adders. And why, if you wish to go down the digital circuits route and you like this sort of thing, then maybe you should be looking into that. But if you look at this and you, I don't know, not, then that's fine. By the way, too late, I started to erase what I wrote on the board earlier. Okay. So the problem here is that the ripple carry adder requires the previous answer before it can move forward. But it only requires the carry. Notice it doesn't require the sum necessarily. It doesn't require the sum from the previous adder. If you look back here, the only thing that needed to be forwarded was the carry. So if there's some way we could pre-compute the carry quicker, then we could improve performance. In order to get to this using the carry lookahead, we're going to have to start editing a couple of things with the way we do addition. Then we're going to have to apply some good old math, and then something's going to pop out. Good old math. So they came up with something called the partial adder. And the reason for this is you first need to think about, from a full adder, it's now going to output 4 lines instead of 2. What they're doing is they're breaking apart the carry bit into what's called the generate and the propagate. So the generate means that the carry was generated because the 2 inputs B and A were 1, so obviously that generates a carry always. So that generates it. The propagate happens when, what do we got? Yeah, when either A and B are 1, or actually, yeah, propagate when A or B is 1, and then the carry bit is also 1. But we're only going to look at the propagation when B or 1, B or A is on. And that'll make some sense at first. Let me draw this up on the board so I can show you why this logic still makes sense, even though I completely erased that. And why is this backwards? Why does the left one go to the right and the right one go to the left? Huh. Well, I do know the answer to that, but I'm not going to say it. All right. So notice we're only looking at the carry. The generate is only going to look at the generate part of A and B generating it. The propagate happens, okay, there it is. I wonder why it's missing the other and. Happens when you XOR it, and then you also AND it with the carry coming in. So this picture is missing an AND right there, which is not good. Obviously, the partial full adder is not the entire thing. In order to make it a full adder, you still need to work with the gate and the propagate. So the gate with the generate, the generate and the propagate. Yes, please, loud and proud.
Man, I'm just enjoying myself here.
Good. I'm glad.
Is that sarcasm?
Me? No, that was actually not sarcasm. I generally want you to enjoy your time here. But if you have a good joke, please tell me. No, okay, good. Anyways, so the generate, also it's coming from the propagate, which is, notice that it's this should be the C out, which is, C0, and the propagate ending coming in. Now this is what's needed to change your partial full adder back into a regular full adder and move it on. Notice this breaks the S functionality apart to generate and propagate functionality. And that's why this picture is actually correct, because this AND is going to be shifted to after the propagate. There we go. We're just including this XOR. So this AND right here is going down here, and this OR right here ended up going right there. So we really just broke apart our full adder from our 2 half adder design that we had beforehand. Now, does this improve performance any?
Probably.
Well, okay, why?
There's a lot of gates there.
There's a lot of gates. Well, we didn't, excuse me, we haven't changed the circuit. We just rearranged it so it's easier for us to look at it. If you notice from back here, or let's go from this picture, we're putting an OR and an AND down here. That signifies this OR down here and this AND right here. This XOR is still there, that XOR is still up there, and this AND is still down there. We haven't changed the circuit. So it's the same performance as before. Doesn't dissolve, we still, doesn't resolve anything, we still have carries. So instead, let's go start thinking about carry in terms of gate, generate and propagate, and maybe that can help us out. All right, well, ooh, where did this come from? Well, let's take a look. So if you're, let's see, chilling right here, in terms of generate and propagate, what's this value? We'll call it C1. It equals, well, what does it equal? It equals C naught down here, and propagate naught or 0, and then you're going to OR that with the generate. Right? It's math, so we don't need the parentheses. Okay. What's C2? Well, it's C1, propagate of 1, plus the generate of 1, right? Well, we have C1, so let's go plow that in there. Okay. Let's go put that all together. All right. Nothing yet. Maybe. How about C3? Well, it's the carry of 2, this one, plus the propagate of 2, whoops, plus the generate of 2. Do y'all see how I'm getting at least the initial terms? Right. The slides are going to do this for me. Oh, I'm sorry, people online.
Oh, I think there's going to be some algorithm stuff going on.
Yeah, there's going to be some mathematical trickery going on.
If I understand correctly, are you basically making it so you can solve for the initial?
Well, the problem is, in our current design, it takes 4 times 6 to get to here,
Yes. 24
cycles. But we've just broken propagate and gate. Is there any way we can rearrange this giant formula right here so it takes less than 24 cycles? Because we've mathematically set it up that this is what C4 is. This is what C4 is going to be. And so is there any way to actually set it up? All right, well, let's go take a look. Well, we play a bunch of math. Ooh, look at all that. That's a lot. So the generate from 0 to 3. Oh, how do they get rid of those propagates there? Oh, they're anding it. So, in other words, group carry generate, that's the group. Notice that now they're just saying it's G3 or the and of this or the and of all that or the and of all that. They're not, this is not a simplification. This is not a mathematical simplification. They're just signifying that G sub 0 through 3 is all this, and P sub 0 through 3, C0 is all that. All right, now think about this. We have, what would be the gate delay of this circuit right here? Well, let's start at the other end. 1, 2, 3, 4, 5. It's a 5 input AND. What's the gate delay of that? I think that's 6. Okay. What's the gate delay of, this is all an AND. That's a 4 input AND. What's the gate delay of a 4 input AND? 4. Are those happening in parallel?
Aren't it?
Yeah, those two are,
Oh.
because they don't depend on the output of each other,
Okay.
right? So I'm going to write that up on the board as 6-4 underneath so we can see that it's happening in parallel. All right, this is a 3 input AND. What's the gate delay of that? 4. This is a 2 input AND. What's the gate delay of that? 2. Nice. And we're not going to worry about that. Well, this all goes into a giant OR, right? And then we have a 0, of course, for G3. And that's a 5 input OR. What's the gate delay of a 5 input OR? 6. And that produces our C, C4. So what's the total gate delay now?
12.
12, as opposed to before, which was more than 12.
Yeah.
All right. So what does this look like? Nice. So, well, this picture makes it look just fine. If I tried to draw this on the board, it would be terrible.
Just awful.
What are you talking about? You got lines. Look how straight those lines are. You got some curvy bullets, some pointy bullets. Everything's cool.
Each one has an extra set of end. Because every time you go one more, you got ends. Right?
So this is what's important to see, is let's go look at the first carry. You have an AND, 2 input, plus an OR, that's 4 in total. You really didn't get anything from that one. How about this one? Well, 2 and then 3, well that's 4, and that's another 4, that's up to 8. 8 is twice as 4, so you really didn't pick up anything to get C2 to happen any quicker. So right there, it doesn't look like this is helping you. On the next step, it's going to. Because this is 4, this is, oh, actually that's 2 input, that's 4 still. Goes in, so this is 4, goes into an OR, which is a 4 input OR, which is also a gate delay of 4, which is 8, which means that this C3 calculation took the same amount of time as the C2 calculation. So there, we got our first speed up right there by using this. Down here was that 4 input is 4, 2 input is 4, 3 input is 4, 4 input is 4. Okay. Goes into a 4, is that also a 4 input OR? Yep, a 4 input OR. So this was 8 as well, which was the same as C3, the same as C2. Now, hopefully you can see that I can carry this out ad infinitum as many times as I want to. And so this gets a huge AND structure. I'll tell you right now, the next one's going to jump to 12 because these ANDs now need to go to a 5 input AND. But if you look at it, what's doing is this structure is taking all the information previous and then computing based on its previous data, all those previous lines, what the carry is going to be. And that's why it can actually compute it a little quicker. Now,
Is it because you're using the benefit of having multiple gates in parallel?
yes. So does this design have more gates or fewer
It has a
gates?
lot
Or the
more
same?
gates.
It has a lot more gates. So this one is going to consume far more area, consume far more power, but is able to reduce the gate delay, which will improve the performance of your circuit. So we just made it bigger,
Okay.
and that somehow made it faster. But
You
anyways,
really don't get your benefit until you start getting into the further on bits.
for
like
this one,
higher.
yes.
Okay.
Hopefully you can see when you get to the 64-bit one, that
Yeah.
last one is not going to take that long, except your first one is going to be 64 ANDs,
Yeah.
all taking what, 64 inputs?
Yeah.
And those all feed to a 64-bit OR.
Okay.
So what would that be? For the 64-bit AND, was that 32, 16, 8, 4, 2, 1, so that's 6 times 2, which is 12, plus another 12, so that'd be 24 gate delays in order to compute the carry for that last one.
Yeah. That's still better than.
It's faster,
Would-
but that's a
ridiculous.
huge cost in area.
In terms of gate delay, that's better than the other one.
Right. Yes.
With the gate delay is 6 because you multiply 2 by grade being the 2 sets of
6, 4, which one? I'm sorry.
for one we did an example.
This one right here, or this one?
The gate delay is 6, I'm asking just.
I'm sorry, there's two
what's the
6, there's two 6s.
I'm sorry, yeah, the gate delay, the 6 in the side, the,
In the, or,
or,
right, this, oh, I'm sorry, you know I drew that poorly. There we go. Right, so it's a 5 input OR, and so if you draw that out, 1, 2, 3, 4, 5, these first two can go into an OR, these two can go into an OR, sorry, I'm kind of out of room. These two go into another OR, which then feed into a final OR, which that initial one that we had, right? And that'll do a 5 input OR, okay? So these two are in parallel, sequence, so 2, 4, 6.
yeah, all right.
Sure.
Gotcha.
All right. And ignore that. That calculation is based on different gate delays. A lot of people like to calculate gate delays as if each gate took 1 cycle, which I hope we have shown early in this class is not accurate. All right, everyone got that?
Loosely.
Perfect. How are we doing?